So thanks, Alan, for your point there about your assignment. It's closed off. Like with all of the other ones, if you can send a message to someone tonight, but if you can't get access to the things, then email them through to your teacher. Thank you for starting the recording there, Glenn. Brett's just ducked off for a few minutes. He'll be back. So I'm pretty sure I'm sharing my screen now, and I thought I'll get started onto the evening's work. We do have a little bit to go through tonight, but it's not too bad. We need to make sure that we have gone through and given you all a good understanding of the things as we go through. So I'm just going to backtrack to last night's lesson a tiny little bit. I'm going to go back. If you just watch the screen for now, so you don't get too confused, and I'll go back to S6, last night's lesson. And I think Glenn was going to put up a document there. Was this the one, Glenn, that you put up there that was a little bit clearer to read? I think that's probably the one that had the drawings a little bit clearer, particularly down the bottom. Yeah, I think that's probably just a little bit clearer.
No, that's last night's.
That's last night's.
The one down the bottom of last night's lesson. I've just put it down there, and it's got student. That's it. That's it.
Here we go. Okay, so down the bottom of last night's lesson, I'll actually open that up for you so you can see that a little bit. That student one, so that you can see that from last night's lesson, because there were some things there that were a bit unclear. And I wanted to spend a couple of moments just going through this and explaining to you, because we did go through this fairly quickly and then I left you all to it, but there were some quite hard questions down the bottom. So I had a few people said, can you please give us a bit of help with this one? So I want to just drop down to the bottom of it and go through just a couple of things. We are covering them again tonight, but want to emphasize that to do some of these calculations, you are going to need to do a little bit of outside research. The comment made in the classroom here last night was, boy, pity anybody who wasn't here in the classroom last night, because we were working through these complex calculations. And if you missed the lesson or you didn't get to have the discussion afterwards, it could be quite hard. So, for example, with some of these, you're going to need to go back and refer to the information that was in the particularly in the build right document. So there's I'll probably put it right up the top. Actually, I think I already may have put it up the top. I'll put a link up in the top here for these build right, because there's a real good site there that shows you that where we get most of our content from. And I've just got it saved on Internet Explorer, and it comes up here so that I can quickly see where it is. And in this particular case, we're dealing with stress and strain. So if we come over to our little build right website that's accessible each night, there's a link to that. It's called Build Right. Then we're able to find most of these activities are in here. Okay, so it deals with the different loads and things like that in this particular site. And the one that we were dealing with there came up with spoke a bit about wind loads, and then there was some calculating of the loads, and there were some examples there of how to calculate the loads. And then for the last part that we were talking about there with our this particular forces and stress and strain, I think that came up down here. There's stress and strain, and there were some examples here of that, and there were some formulas that we needed to be aware of. So for example, right here there's a formula, and the stress is the force divided by the area. And then there's some activities right down at the bottom here, which goes through some topic activities. And these are pretty much what the exercises that we came up with, that have been come up with for the activity that you're dealing there. I'm just going right through these to find, I think it was one of the last ones that was on here. There was an exercise here that dealt with working out objects and things like that. They've been one of these ones. Okay, so these kind of deal, you're going to need to do a little bit more research into some of these areas just to be able to answer some of these questions. So for this particular one, we looked at that post and we had to work out the area that was being exerted on here. We also had to find out in this case it was a hardwood timber post. And last night we spoke about the fact that there's an Australian standard that tells us what the what the weight is for average for hardwood timber posts, and it's on one of the Australian standard documents, and it was throughout your notes and things, and I think from memory that was 11 kilograms per cubic metre. I think that was the one that we dealt with on that. And then, so what all we had to do was find out what the area was that's for this post, and then we had to calculate that through and work out what the compressive stress was. So I'm just going to jump back here to where I had the answers for this one and just talk about this briefly. So I had some worksheet answers for this one here. And so this will help you with your last one that you had last week. And there's an example of it there. So for this particular case, the formula was stress equals force or the load divided by the area. And the load for this one was 5 tonne, which is, if you work in this particular case, if we work on 9.81 kilonewtons per that's the gravitational acceleration, you'll come up with 49. So we did the calculations on that one last night, and so we went 5 times 9.81. I think that's the one where we come up with 49.05, which is where we got the 49 here. And then the area of this is in this particular case 250 by 250. So if we clear the calculator and we go 250 by 250, it'll give us 62,500 millimetres squared. You'll notice here we're dealing with millimetres squared instead of metres squared. So you just need to make sure that you're converting them all okay. And if you do the maths on this, 49,000 newtons. So we need to either bring them all to kilonewtons or all to metres squared. In this case, we brought them all to newtons instead of kilonewtons. So if we go 49,000 divided by 62,500, 62,500, we get 0.8. If you reduce that back to one decimal place, that's 0.8 megapascals for that particular activity. Okay, so that's recorded, and that's one that's at the beginning of the recording here tonight. You'll see that'll come through if you get stuck on something like that. And it's just this formula here: stress equals the force or the load, which is 5 tonnes. But that tonne load, it'll normally either be kilograms or tonnes. It needs to be multiplied by gravitational acceleration, which is 9.8 or roughly 10. We often allow 10 kilonewtons. And that's, remember, Newton with the apple that fell off the tree. So if we multiply that by 10, you get 50 kilonewtons there. And then there were some earlier exercises and things as well, which I'm not going to go right through here tonight, but I did want to spend a time on that last one. And then I want to go on to tonight's work, which has an extension of some of those exercises. Now, some of this is a bit mathematical, and you are going to need to do a little bit of outside research, possibly, to be able to complete them. So one of the first things that we need to get you aware of before we get too much into the notes tonight is the fact that there's an activity there for you tonight under S7 lesson where you need to start thinking about your final exam location. So on the last night, apparently there'll be a 3-hour exam. Brett was saying that we'll be starting at or opening that up at 4:30, and that's an exam where you're going to basically compile answers for all of the work we've done through these units, and that potentially could be a 3-hour exam there that you'll need to, and you just need to jump on and specify where your exam location is going to be. So we've put in there an option for all the different ones just so you can make sure that you're there somewhere. That would be a real good one to go into a classroom to be able to do, because it's highly likely that you might need a little bit of clarification on something here and there. If you can't do that though, then definitely make contact with your teacher, and we're planning towards having that on the 28th of November. So let's put there the 20th, that's a Thursday night. 28th of November is the plan for that one. It's the last Thursday. So by then you will have done plenty of practice on the exam, and you should be able to just go in there and do that quite quickly and quite easily. Well, not necessarily easily, but you should be able to do that okay. So that'll be a summary of all the work that we've done for this block of units. you'll see as we get going, because we're going to do plenty of practice at it, you'll see as we get going the types of things that'll be in that that exam for that night. So hopefully that's all clear for you. Jump on there, and that's your first little green completion box. Once you tick in there where you plan to be. So I'm going to spend a little bit of time tonight now looking at live loads and some calculations, and I'm going to open up a couple of activities, and then I'll leave the submissions for this until we get a little bit of work done. So a couple of other things done, and then most of tonight is just going to be going through and answering some of the questions and things and working on getting these completions. So it's pretty straightforward there tonight. Not a lot of new teaching to go with it, just a little bit on one particular category. So here we have a worksheet, which was similar to what you had last night, and you should be all fairly competent with this to be able to calculate the live loads for the dance floor. Now, once again, you're going to need, with all of these loads, you're going to need to be able to access the codes that tells you where the loads and things are. And you should all be able to use your TAFE username and password to be able to access the codes. And you'd probably need to make a note somewhere of all the different standards that relate to construction. And you can see I've been looking at a few today. So actually the loads one's not there, and I think it was 1170 from memory. It's quite hard to find them, but if you type in just the search words and things, you'll be able to find the codes that relate to us. So structural designs, this is 1170 2002. That's an amendment. So this is the one I want right here now. Some of these I have put on here, so I'll just check if I've got them on there. Looks like I've already got 1170 on here, what I had before, so I might open it on my document here. You can see on here we've got our different loads, and we have information on here about what the different loads are and how they've been calculated, so that we can just look at a chart and see what the different loads and things are. There's tables here that show us the loads. I did have it written down earlier what the table was. If somebody could just type that in there if they find the table. I think it was quite early on. It just showed us the table which relates to the different loads. And it pretty much gives us the different parts of a building, and someone's gone through and measured on average what they are, and they've put it in there for us. So I'll just type in there whoever finds that first. So it says here, this section gives permanent actions for designing structures, permanent structures, and it says calculation of self-weight, provision. Nobody's typing in there, so we'll just keep working our way through. Australian Standard 1170. If you could just turn your microphone off when you come in, please, everybody. So we've got here reference values of imposed floor actions. This is pretty detailed. It's much more. There's much more loads here than what there was on some of the other ones. I'll just mute everybody here. Oops, participants. Okay, can you still hear me there? Sam, you got me still, hopefully? Yep, so I'm all good. Okay, so I've gone to Australian Standard 1170, and it's got loads. It's got way more than what we actually need for our exercise here. But we were working on a load chart last night and the last few nights. If somebody can find where that is, just type it into the chat box and we'll access that. Imposed actions, concentrated actions. So I'm just going to go back to my question here. It says calculate the live loads of the dance floor. So I'll do a bit of a search here for the word live. Live load. Dead and live loads. Here we go. Codes of practice for general construction design. Has anybody typed that in there yet? Nope. This talks about that's not going to give it to us. We'll jump back over here to standards. Do another quick search here. loads. Student notes has it in there. Document that was up last night had it in there. Can you find exactly which standard had a listing of our loads? So, oh, here we go. So we've got 1170 there. So with this document here, the dance floor was 5. So what we had, I just remember it from the code there. So 5 was for a dance floor. Normal buildings is 1.5. And someone can do a search for the standard and the code of where that is. There's a table there and they'll be able to find that. So if in this particular case, if we had to, if you have to actually submit one of these, so you can just grab yourself a text box, just go insert, grab a text box, move the text box to wherever you want it. Generally with the text box, if you right click and place it so that the text box, in this particular case, if the text box is in front of, or if it's a tight fit, then you'll be able to type things in easy enough and you can put your answers in there. So in this particular case, we have to find the area of floor, and then we times by the kilonewtons per meter squared, and that equals the load. So you just do that little calculation. This is pretty straightforward, 4.8 times 6.75 equals, and someone can type into the chat bot what that equals there. Quickly do that one, 4.8 times 6.75 gives us 32.4 kilonewtons. Sorry, come on. That'll be the total load is 32.4 kilonewtons. So we've got, oh, sorry, that is the area. Yes, you're quite right there. Thanks. So that's your area. And then what we need to do with this is then multiply that once again by our kilonewtons. And in our particular case, that's 5 kilonewtons per meter squared, which gives us, which I haven't done, times 5 as 162. Is that right there, Kamal? Kamal said 160. Kamal's called out 160. So you put in there what your answer is. I think I had a different measurement in there. Oh, I had 162 for that one. 4.8 times 6.75 times 5. I got 162. Oh, 30. So I had a different measure there. So you get the concept there, and that's the sort of thing you need to do for each of these activities. And there's a group of these tonight. This is one of them. And then when you look at the live load for an office, you'll be able to find what that loading is. Someone's going to type in hopefully the code. Someone can type in the code of where the loadings are. We can find that an office, it has its own floor load. And then a bar floor, it's got its own load measurement as well for a live load. And at the rear of a house, it has a loading of 1.5. Normal housing is 1.5 kilonewtons per square meter. So we need to find that and put that in there. And that's one of your first activities that you're going to do tonight. So that's pretty much going to bring you back into being able to complete some of these things. That's the first activity. And then there's a spot there for you to be able to upload that. Then there's another one there for dead load, and there's a spot for you to upload that. And then I'm going to open those up for you in a little while, and you can work on those and get them complete. So any questions about that at all? I can see Mohammed's got a solution up there for us for that standard. I'll just grab that and open that one up. Thank you for that. Okay, the Australian standard was 1170. This is quite good actually because it gives us a table, so it's 1170. Which table does it say that is? There's a table in there for 1170. I'll go back to that standard and find that one for you. Go to the office one. Offices and workplaces. There's a real simple table that had all of this on there. Okay, I might have the wrong standard open at the moment. So you've got the link in there for that. You can all work your way through that one. And there's a table that, thanks a lot for that, Mohammed. Now, all these documents that you can see on here, that's helpful, but we really want to go back to the source document, which is Australian Standard 1170, and I might have to find the right one. Some of them have a .1 or a .2 or a .0 after them, and we've got to just find the right one for that. So that's your activity for in a little while, is to work your way through those until you become quite confident with them. Now, what I want to do now is spend a little bit of time talking about load paths. And the first activity we've got here for you to do, to grab another completion bar, is type in here what you understand by load path. And we talked about this a little bit last night. And this particular case, we're dealing with a building that's a residential and commercial class 7 car park building. Where does it start and where does the load finish? So type a discussion in there about load class. Can you all stop talking, please? They're talking a lot in the background here. So we want you to have a bit of a look to put a topic in here about what you understand by the load path of a building. Go for it. And then I'll jump back and have a little look at that in a second and see what you've all put in there. So just it's 5:53 now. I'll spend about 2 minutes. Put in there, and you can get a green completion box. Put in there what you believe to be the load path, what you understand is the load path for a building. Another minute, and then I'll check what we've got on there. Okay, we'll have a bit of a look and see what you've got in there for load paths. I can see we've got a whole bunch of points there. Let's start at the top here. Kieran has load path is simply the direction in which each consecutive load will pass through connected members from the highest part of the car park all the way down to the footings. That's great. That's real good. And Callum's got here, load path is the path that the load takes. That's very good. There's load path. That was an easy green square, wasn't it? It's going to be the direction in which each consecutive load passes through the connected members. Very good. On here, load passes a transference of load from the top level or roof down through the structural member all the way down to the foundations. The use of beams, that's real good. So that's great. You can keep on popping things in there as we go. That's real good what you've got in there, and that's great. So that's load paths. Now, what we want to do now is have a quick look at this. This is going to take us to our Build Right toolbox once again. And once again, I've said to you that if you don't open this in a browser that supports a Java type thing, then it's not going to work. So I put it into Internet Explorer and it works good for me. But if I do it in any of the others, the pictures and things don't come up. And we've spoken about this a little bit before, and I've shown you the load paths, and we've looked at how this works. Remember, we talked about that last night, and it shows you a diagram of how all the loads path all their way down through the building. And that's what you're pretty much talking about just there. So that's covered that one real good. I've opened that one up for you. Now, we want to also have a look at Australian Standard, and here's a picture from the Australian Standard. 1684 clause 1.7, and I want to highlight this for you. So in Australian Standards clause 1.7, there's a part in here that shows you the load path. Just bring that back down so we can see that. This is at the beginning of the Australian Standard 1684, which you should all become pretty familiar with as we go through this. So it says here, load paths, offsets and cantilevers. Where applicable, roof loads shall be transferred through the timber frame to the footings by the most direct route. That's real helpful for us because as we do our structural planning, we always want to try and take it by the most direct route. For floor framing, the limitations imposed regarding the support of point loads and the use of offsets and cantilevered are specified in Section 4. Section 4 is all about floor framing. So the notes are real important and they give us some information there, which relates in this particular case to a couple of figures. So here's a couple of figures. Let's have a look at them. This first one here is figure 1.4, and this shows us what the term backspan and cantilever is for, what they mean. Now, as we go through this standard, when we start specifying buildings and things like that and all the structural details, it's going to use that term backspan and it's going to use that term cantilever. And we need to make sure that this is the diagram we go to be able to find what that means. You'll find here that on the Australian Standards, the very first chapter, which is this one, because it's got a number 1 next to everything, figure 1 or clause 1 or table 1, that's the first chapter. It deals with defining everything and saying what things mean. So if ever you see the word backspan, which you will, you need to be aware that's what it means. Okay, and cantilever, that's what that means. That's pretty easy to understand, but backspan's just a little bit harder. Okay, so there's cantilever. In this particular case, we're allowed to, where there's a diagram there that shows us what offset means. So in this instance, if we've got our roof load coming down here, it doesn't have to go directly onto the joist and then the bearer. It can be a little bit offset, and in fact, it's allowed to be offset by 1.5 capital D in italics maximum. So capital D in italics right there will be defined somewhere. It'll be shown somewhere what that means. And pretty much when you see a D like that, that'll mean the distance. Okay, it's like the measurement. So we're talking there 1.5 times D. The member designed as not supporting the load. So here we've got our joist. If it's designed to support this load, then that load can go anywhere. And obviously this joist is going to be a much bigger beam because it could fall somewhere outside of that 1.5D. But as long as that roof load stays within 1.5D of this support that you can see highlighted, then it's going, this member through here doesn't have to be designed in such a way as to support the load. Okay, so that's an example of what that talks about there. And back on our course here, I've opened up that load path, and you can see that's a little pop-out window that shows you that example and how that works. And there's a bit of wording and things there as well. So that's just a quick way for you to be able to get to that. Now, I need to you'll see tonight pretty much I'm just going to talk a little bit about load paths, a little bit of an introduction to Australian standards, a little bit more on wind loads and things like that. You've got an activity down here for designing of floors and walls. There's a little bit here on building masses, a little bit on wall systems, and that's pretty much it. So I'm going to just jump back here to this and open up this next thing here, which is the Moments Build Right Toolbox. And once again, we've got that Java thing there, which most of you will come across. So I'm going to open it up in my other browser here, which I've got open, and make sure that I go to this one, I think it is. We'll just go forward on there. I did have Moments up there a second ago. Go back on here. I think I had, there's our Moments. So Moments has an introduction. I think I may have already talked to you a little bit about this, but on this toolbox, we're pretty much going to be introduced to 3 new terms. Okay, now I guess a good example of what we're talking about here, and thanks for that, Josh. I'm going to make a note of that table there that Josh has just said 1170.12002 3 table 3.1 page 9. Thank you for that. I'll have a look at that in a second. So I want to tell you, can you guys stop talking here, please? I want to introduce you to something here in a second that's really relevant for building, and that is that a thing can have a certain weight, but if it moves away from its immediate support by a distance, then that weight can appear to increase, and it works like this. As you know, I went to Lake Eyre during the last holidays, and 5 of us turn up at the airplane in the morning, ready for a flight, and we're all different sizes. And the pilot looks at the little plane and looks at us, and then he lines us up virtually. And he says to my wife, "You're in the back, you're light." Says to the bigger guy, "You're in the front, you're heavy." And he says to the rest of us, "You're in the middle." And there's a reason for that. And it all comes back to what we're talking about, what we're going to talk about now. And that is that a particular weight on any aeroplane, for example, or any building or any beam or anything, there's a point where everything's in equilibrium, and everything will just sit stationary and it won't swing to the either up or down. And it's kind of like a seesaw. And what happens is that what you do is the further a particular weight gets away from that center point where everything's in equilibrium, then the more that weight appears to be. So if you hook your trailer on, and then you have on that trailer, you have more weight behind the wheels of the trailer, let's say it's a single wheel trailer, single axle trailer, then that trailer is going to swing around in the breeze all over the place as you start going fast down the road. And the faster you go, the more it'll swing. And you can see some good YouTube videos of how they do that and how they demonstrate it. If you put the weight too far to the front on your tow ball, the same sort of thing will happen. Not as bad, but it can still happen. So the idea is to have the weight in equilibrium right in the center. And that's where we come and we talk about, there's 3 different ways that we can have that weight. So one of them is a point load. In this particular case, what we've got here is a point load where it's expressed as an arrow, a point load on something, and you can kind of draw it graphically as an arrow. So in this particular case, the point load comes directly down on the top plate here and directly down on the top plate there. And then the next type of load that we can have is a uniformly distributed load. And concrete's a real good example of this. So if we have concrete and it's for, whatever it might be, kilonewtons per meter or per square meter, then it's uniform across there, hopefully, and we're able to allow our weight so that we can calculate that so that we can allow enough strength to be able to support the thing from collapsing. And then the third definition is a uniformly varying load. And a uniformly varying load is where, for example, in this case, we've got a retaining wall, and this retaining wall has quite a bit of weight pressure against it at the bottom, but up the top here, there's hardly any pressure at all. So uniformly, unless you've got some big rocks leaning against here or some other unseen situations, uniformly the weight will decrease as you go up the wall. And uniformly, you could decrease the section size of that wall as you increase the height. You could calculate so that you could decrease it by an amount to save a bit of concrete. And if it's a real big retaining wall, that's what would happen. And that's why you see beams and things that are often quite a lot thinner out on the flange than what they are in the centre. For a beam, it might be quite thin on the left and the right, for example, on a big beam, because there's less forces there. And you can actually draw that force and calculate how much it is and work it out so that you're able to work out what size and what strength you need at a particular point. So there's three new terms that I've introduced to you there: point load, uniformly distributed load, and uniformly varying load. Mostly we will be familiar with point load. You're all familiar with that because when you build something, you have your load coming down onto a point and you put in your fasteners and things like that. But a uniformly distributed load, remember, that's just a large weight that's spread over a big area. Eventually it may come to a point somewhere. And then in fact, when we do our calculations, we calculate as though it is a point right in the center. The first thing we do is we transfer it to a point load, and then we'll find the center and sit it in there. And so the next thing that we need to be able to understand with structures is what I talked about there about moments. And basically moments is the turning effect by a force that's exerted a distance from something. So here's the calculation. Oops, I think I can highlight that. So the force times the distance is going to give us the turning moment, or the amount of force that's going to apply on something. Mouse got stuck there, I think. And there's our little formula. Okay, so if this particular force of 10 newtons is occurring 5 meters out from the pivot point, that's going to be 50 Newton meters. If it's occurring 10 meters out, it's going to be 100 Newton meters. And the further out it applies, the more that force, even though it's still only 10 newtons of force, that's still going to increase more and more the further out it gets, unless there's a prop or a support in here somewhere. Okay, so that's a concept that I want to expand on in a moment with you. And I'll just jump back here and we can have Kamal's hit it on the head there. And so I just want to spend a couple of moments here talking to you about a document that I've just put up today. We used to spend a lot of time on this with structures, and so I've put this up for you with all of its answers and all complete, because you don't actually have to do quite so much of this. And this is kind of like an expansion of that, so that you can have a bit better understanding of how all this works, because it is important for you to understand this in relation to structures. So equilibrium and moments. We're always trying to get equilibrium. If we've got a big fat elephant sitting right near the wall and a person's right out here holding that up, it's not too bad, but they're going to be sweating and straining when the weight comes out further. And that's an example of moments and how moments works. And a moment can be described as a turning effect resulting from a force applied to a distance from the support. Okay, so it's going to kind of turn and everything. And we have a number of different ways of how we can calculate this, but I've put up the simplest one that I've found over the years for us to be able to do the calculations. Not that you're going to do much of this in this course, but this is here for you in case you do come across a question here or there that asks you to do it. So because moments are measured as a measure of force applied at a distance from a given point, their unit of measure is newtons times distance. Okay, moment equals force times the distance from the pivot. That's a calculation right there. That's highlighted yellow because I always said to the students, just highlight that as a calculation. And here's an example of how we do it. Let's say we've got a seesaw, 60 kg person here, 80 kg person there. We've got 2 meters from the 60 kg to the pivot. How far would we have to have from the pivot to here for the 80 kg person for everything to be in equilibrium? And that's the question. We don't really, the engineer designs all this for us, so we don't come across this too much. But can you see that to be able to solve that is going to be able to make our structures in equilibrium? We're always trying to get equilibrium with everything. Okay, there's a little bit of wording there. And if we look at that, we can actually do the calculation for it. So 60 kgs times 10, which is gravity, times 2 is 1200 Newton meters of force. That's 60 kg. So we have to turn it over to newtons, and we work on an average of 10 newtons, 10 as the gravitational acceleration times the kilograms, and so that gives us our force there. And then if we look at that, the calculations are there for you so that you're able to work out that if you go 1.5 meters on the right-hand side and this one goes 2 meters, then that'll stay in equilibrium. Okay, you'll see that this person here is 80, which is about a third heavier than that person, but 1.5 meters is not a third less than the 2 meters, is it? Okay, and so it doesn't always ratio out exactly. Sometimes you move a little bit here and you've had a big impact on the equilibrium, and it's real important that we do the calculations for that. Now that's not so much a building example, but have a look at this one here that I'll put up for you for free. And here is a building example. In this particular case, we've got 10 kilonewtons or 10,000 newtons exerting a force 1 meter out from the wall. And 5 meters out, we've got not a very muscly person holding up that wall quite easily. Then, and we need to do the calculation there that's figure A, okay? And then there's another one here in figure B. So let's have a look at what's happening here. 10,000 newtons times a meter equals 10, that's 10 kilonewtons, okay? Therefore, the reaction the person and person A must produce is 10 kilonewtons divided by 5, which is 2 kilonewtons. So this person's only got to lift 2 kilonewtons worth of force up here. Let's see how much this person's got to lift. By doing the calculation, they're lifting 6 kilonewtons. Okay, so the beam that would go here would have to be a stronger beam than the one would go here, just because of where the weight is. Do you get a bit of an understanding of how moments and things work and how important it is? It's exactly the same weight, but it's just a different distance out. Now, I'm going to introduce you to some activities here in a second. You can read your way through all of those. That's there just for your help. And I'm going to introduce you to some more building examples. So this is a 21-page document here, and you've got a whole heap of examples which you can have a look through and read through and work through. Print it out and keep this as an example for you for moments. And what I'm going to show you now is briefly how we can calculate the exact strength that a beam might need to be using an industry standard method of calculating what the reaction might need to be on a beam. In this particular case, you can consider the following diagram. It examples a simple beam supporting a load of 20 kilonewtons. So we've got 20 kilonewtons down here. There's our beam, and there's our reaction or our support post at A and B. There's the measurements of where everything is. Now, the formula that we use is this simple formula down here. Here it is here. We write it out like this. So there's our case. I've drawn up a little diagram like that. That's the very first thing you have to do, is draw a diagram. It doesn't have to be to scale or anything, but just sketch a diagram of what's happening. And you can see in this case that 6 meters in from the left, we've got a 20 kilonewton load. That means 2 meters in from and then another 2 meters, we've got the post at B. So we've got a post at A and a post at B. And what we have to do is calculate what strength do we need at B and what strength do we need at A to be able to resist it. And obviously both of those strength columns there need to add up to at least 20 kilonewtons. If this one adds up, if both of those added up together only comes to 19, then the whole thing will collapse. So they need to come up to 20, and we can calculate how that works. And this little formula right here is the way that we do it. We basically pretend that we're standing at one end and we do this calculation. So in this particular case, we pretend we're standing at A, and every force that occurs clockwise, we put it on the left-hand side of the equation. Here's the first one. As we come across here, we've got 20 kilonewtons there times 6 meters across, and we put that there. And then the reaction, which is on the other side of the equation, is the anti-clockwise moments. And we've got an unknown resistance of B. There it is there, resistance B, unknown, 8 meters apart. So there's our little calculation. You can all do that pretty easily. And all we have to do is solve the equation. That's just a straight equation. 20 times 6 equals 120. We've reduced that one back and solved it. And then we've got 8 or R8, unknown resistance of R 8 meters apart. And we've just got to get rid of the 8 over to the side over here and get the R all by itself, and we'll find that if we do that, 120 divided by 8, it gives us 15. So that means that the resistance here needs to be 15. So this little formula that we've just done here, that's all we do with these, and it gets real complicated further down on this table, but we're sticking to that exact formula. On the left-hand side of an equation symbol, we put clockwise moments. On the right-hand side, we put anti-clockwise moments. And we first of all pretend that we're standing at a point. So we start at the left-hand side and stand at A and write down everything that occurs clockwise. And then on the other side of the equal sign, write down everything that occurs anti-clockwise, and then reduce it all down till we come up with a number. So if we stand over here at B, the first clockwise motion is A. It's occurring clockwise. We don't know what it is, but we know it's 8 meters apart. And the first anti-clockwise motion, so coming around this way, is the 20 kilonewtons, and it's exerting 2 meters apart. So we write out our little formula like this, just like that. Clockwise equals anti-clockwise. Resistance A, 8 meters apart, is equal to 20 kilonewtons, 2 meters apart. Reduce it all down and you come to 5. So that means we can look back at this and we can say this one here is 15, this one's 5, and then 15 plus 5 equals 20. So that's a real simple one there. I'm just going to check the chat box. Can't you just determine the percentage of the load it is and carry is to carry and work it out? Very, very perceptive, Han. So you can see what Han's done there. He's turned around and said, well, maybe we can work out the percentage of the load, because we're going to attribute a certain percentage to this side on there and a certain percentage to this side on here. And you possibly can. I'm pretty sure Kamal will tell us there is another way. There was actually another way on this document that I put up here, but I know you only want to know one way to do things, so I deleted it and left this one. And I'm pretty sure you can go to an app online somewhere and it'll calculate all this for you, but you're welcome to research this yourself in your own time. So hopefully you understand what I've talked about there. And this is just one method, like we said, but we were able to use that method and solve what the strength we need for the beam here and the strength we need there. And we discovered that we would need a beam that had a column that had a strength of 5 kilonewtons and a column here that had a strength of 15 kilonewtons. That means potentially that's going to be a big column. This is going to be a little one. That's why when you go into the car park of a multi-story building, you see all different size columns and beams and step-down beams and all sorts of things, because someone's gone through and said, we don't care if they're a different size. We just want the least amount of concrete we can have in the column or the beam. And they've gone through and done calculations like this, much more complicated, more like these ones I've got down the bottom for you. And they basically, what they do there is they do all the calculations and just put in the smallest amount of strength that they need to be able to hold something up. So I'm not going to spend much more time on this other than to say that when we draw a diagram like this, that means it's a uniformly distributed load. So in this particular case, we've got a column there, we've got a column here, A and B, we've got a weight down there a certain distance, a weight down there a certain distance, and we've got a uniformly distributed load here, and we've got a hanging cantilevered bit out here. Well, the first thing you do with uniformly distributed load is turn it into a point load. And if that's 2 kilonewtons per metre and it's 2 metres, that's going to be 4 kilonewtons right in the centre. Okay, unless we're allowing for live loads, which might be a greater load out the end. So in this particular case, we've only done this for point loads and uniformly distributed loads. And so we just cross that out and put 4 kilonewtons right in the centre. So it's 1 metre out. And then you can do that exercise, and it's all been done there for you. And you can do that the same as the others. Now, I used to do an exercise when I did it in with my class, and I'd say each person just draw a scenario with a couple of beams and just draw in there whatever loads you want. Here's a couple of difficult ones that we've used over the years. Look at these, and you can use the same principles to be able to solve all of those, and you'll be able to work out what the strength is of the column that you need there. So I'm just going to show you, excuse me, once again where that's found. So that's on tonight's lesson, S7, and you're welcome to download and have that. And that, I'm hoping what you can gain from that is that to see that when engineers design things, Everything's very specific and very exact, and they design it for a reason. And here's, you can hopefully appreciate, even if you can't do all those calculations, you can appreciate that reason and be able to understand that when we see somewhere written on the truss instructions that it says use a 30 mil long by 0.28 by 2.8 diameter certain type of metal nail to nail 3 into this side of one side of a triple grip and 2 into the other and 3 into the other side, that's exactly what you need to do. Don't just pull the clouts out of your nail bag and use the ones that you were using for the last job, because somebody's gone through and done the special calculations like this on why you need to use those particular types of nails, and that's hopefully what you come up with. So just real quickly, here's another chance for a green box. Jump into this little discussion topic, and just without checking too much on what I just talked about, see how good your memory is as to what a point load is, a uniformly distributed load, and a uniformly varying load. And let's have a look at what you put down for that. At 6:22, I'll jump back on in 2 minutes and see what you've all been able to put down for that. Just let's see how good your memory is. So don't go back to check, just put in there what you understand by those means. And if you're not sure, leave it blank so we know to go over it a little bit more. Okay, 6:24. I'm just going to get this next bit ready and then we'll jump back in and have a look and see what's been put in. Just keep typing in there. You get yourself a real quick green box for that one. Okay, we've got the first one there was Lachlan. Let's have a look at what Lachlan had to say. Load on a point, load evenly distributed, load of varying uniformly over a section. Yep, that's good. Okay, Dan says here, point distributed across a known span, distributed evenly. Evenly is the key word there. And this time, multiple different forces, yeah, but it varies evenly across the span. Okay. If you think about a cantilever, that's kind of like a varying load because it's less load out towards the end. So we've got here, I went through Lachlan's there a second ago. Let's have a look at Jai. Yep, weight is distributed over 2 or more members. The weight is can be. It's just that it's got to be evenly distributed. And if it varies, it'll normally vary evenly. Okay, they're the terms there, and we'll have another one here. You can see point load is a load applied at 1 point on a structural member. That's real good. Everybody's got that one real good. And if it's uniformly distributed, it is loaded at equal amount right across, okay? Uniformly varying load is unequally, so it's going to be more on one end than the other, but it normally varies evenly in its increase in load or decrease in load. So that's real good. Now, 626, I'll just keep on going here with the Australian Standard, and I want to open up for you. Have a look at how the Australian Standards use. I'm just going to be real quick here for this section because we're going to spend a lot of time living in the Australian Standard 1684. You need to make sure that you've downloaded that and got access to it. There we go. There's a Word document here that's been put up for you of the Australian Standard. Now, whether it's exactly the latest one, I'm not quite sure. You pretty much always should go to the Australian Standard site to be able to get the latest one, just in case they're a little bit out of date. But if you look at the Australian Standard, it pretty much follows a number of different paths. So we've got 1, 2, 3, 4 design criteria. So we've got non-cyclonic areas, cyclonic areas, and there's a simplified one for non-cyclonic areas. And the information in this Australian Standards relates to for timber framing code, obviously relates to timber framing. Okay. Now there's a heap of I'm going to show you these videos, but there's a whole heap of videos which go through, and you can look at in your own time. Goes through a bit about a summary of the Australian Standards. But as much as anything, you're pretty much just going to have to jump onto the standards and start looking at them to be able to fully understand them. I'll just draw your attention real quickly to how specific these Australian Standards get. If you look at this example that you can see I've popped up there on the screen, this tells us exactly the type of nails that we need and the type of looped strap that we need for this particular fastening system. Okay. And this has gone into tie downs here. I'll just move on into wall bracing because it's probably a little bit more understandable for you. I can't get my little bookmarks up on the side here at the moment, so just have to. I'll just jump back here so I can get my bookmarks up. There we go. There. That's a bit big and a bit small. So we're going to live in here, but I just want to show you one example of some bracing. If you're getting a bit dizzy, just shut your eyes for a second while I get to the bracing. So here's what I want to spend a little bit of time looking at. I just want to show you, actually, I won't spend much time now, but I want to show you how specific this is. So in this case, this is where you see your terminology starting to come through. You can see here that this type of bracing, which is a type C, timber and metal angle braces, is going to, if we build according to what's shown in this little table here, this is going to give us a kilonewton strength capacity per meter. So that's per meter run of the wall of 1.5 kilonewtons. We're going to be able to achieve 1.5 kilonewtons. As long as we do what's written here. Okay, make sure no notches exceed that. Make sure we use 2 50 by 20 by 2.8 diameter nails. Okay, or the other alternative. And we do all these things specifically mentioned there. Also checking the detail for above and below for the tying up of the bracing. And that's an example of how we have to be real specific. And so why I showed you those difficult calculations before is that this type of information that's available to us takes into account all those calculations. And if it says we have to use 30.8 millimeter galvanized iron strap to each corner of the bracing panel, tying studs to plates with 4 2.8 millimeter diameter nails each end, that's the sort of thing you'll see on the engineer's drawings for a job. That means exactly what you use. They've got to be galvanized iron strap, got to be 4 2.8 millimeter diameter nails each end, and you've got to do it exactly according to that, otherwise potentially the whole thing won't stay up. And to build towards all of that, we talked the other day about the wind regions, and so I'm not going to go into any more of that other than the fact that we talked about how Australia is divided up into wind regions, and then We talked about Australian Standard 4055, and I think that's a part from it showing you one of the tables. In this particular case, once we go through our 4-step process, we're able to come up with an N number or a C number, a C letter. So an N letter, N or C, might be 1 through to 6 of N, or C 1, 2, 3, 4, and that'll give us, when we have that N or that C, that's what we use when we go to our tables to be able to determine what sort of nails and what type of bracing is required. Okay, so it all leads towards that. Here's another chance for you to get another little green box. In this case, we're just asking you to quickly type in the chat box, if you live in Cairns, which Australian Standard 1684 part should you use and why? Okay, use this information with the C. Find this information with the National Construction Code. Tell us where you found it. So you can either look on Australian Standards 1684, but if we live in Cairns, which part of the are we going to need to use? Which part of the code are we going to need to use? Somebody type it in there and let's check you. 6:32. Let's spend 2 minutes on this one. Get yourselves a green box. We'll get a bit of an answer and we'll move on. Cyclonic, yes, Josh. Type it into the discussion topic and tell us which particular part. So it'll be AS 1684 part something or other. Tiny little hint was this little box that we called up there a little while ago. I'll do a little refresh and see if anybody's popped anything in. So Lachlan said 1684 Cairns, the badge goes to Lachlan as being first. Cyclonic, why would we use that one? How do we know it's a cyclonic area? Because there's cyclones there regularly. True. I asked for that. I'm logged out. We'll jump back into there. Tell us why, and we'll jump in there and check that in a second. I'm just going to fire up Australian Standards once again. We've got our Australian Standards there, so I'm going to fire up Australian Standards again. Remember, you can all access these. This is where you need to get your information from. I'll just fire up 4055. While we have a look and see what you're all saying. Let's see who else has popped something in there. Looking for Callum this time. We hadn't checked you before, Callum. So we got, that's good. Part 3, cyclonic. What do you reckon the difference is between something that's cyclonic and non-cyclonic? We've got Lachlan's, we've got wind in the background here. People are telling us. So that's real good. Coming through there, 0.3. 0.3, yep. So that's all good. You're getting some good stars there. Just have a look and see if I've found wind loads on housing. Here's our 4055 2012 wind loads on housing. Once we fire this one up, you'll find when we look at the map of Australia close up on the Australian Standard, we'll be able to see that it comes up as it's real early in this document. There's a map of Australia. Skim down here to the map of Australia. Here it is. I know it's on its side and it's probably going to be a bit awkward to turn it around now. That would be real good though, wouldn't it? Let's just save that off there. Fire that up. Here we go. We'll rotate that around to the right and go down to our map of Australia. So you can see here on the map of Australia, Cairns is listed up here. That's Cairns and it's drawn in the dotted area. And that dotted area is called Region C. So imagine there's going to be something that tells us about region C. The striped area is region B. The rest of Australia is region A. So if we have a look down the bottom here, there's going to be somewhere that tells us a bit more about region C. And obviously when we start choosing the region, which is the very first thing we do with our wind load, it's going to, that's going to be the first thing we write down. You can see here, it says the first thing we do is work out our wind region. And once we have that, we put that into our little table, which is going to be this one here on the left-hand side, and we go straight to region C. So you can see region C is all of the answers for region C are going to be a C1 to down to maybe a C4. And there's a few there that are not applicable. If your terrain is too open, you may need to get an engineer. It would say, it'd tell you about that at the beginning of this standard, but the worst case scenario, you might have to get an engineer to specially design something for that particular situation. Okay, so that's real good. You've got yourselves another green box. Now there's an activity that's coming up here in a second, which I'm going to open up as soon as I finish this little talk here. Just want to show you a couple more things and then I'll come back and open all these up for you. So this next part here is to is going to talk about building masses, and we need to have a look with building masses at 1684.4, which I had open here somewhere for you. 1684.4. There it is. Hopefully it's not all green. And when we open up 1684.4, it's going to have it's going to talk to us about a bit about building masses. And so there's an example here where it talks about all the different masses of a building from the point of view of the parts of a building. I'm just going to open that so you can see that activity there. But if I go to page 10 and 11 on this one, duck down here to page 10 and 11, we've got building masses. I'll just do a quick search for it. I think that's where I found it. Yep. So here's your building masses, and we come down here, you'll find that in the Australian standard, it gives us the building masses that this standard's going to apply to, and we've got table 1.2. This is pretty specific. So this tells us that joists, bearers supporting floor loads only has an approximate building mass there of 40 kilograms per square metre. We can convert that back over to kilonewtons and use that in our table if needed. We also have bearers supporting load-bearing walls, and it talks about amounts there as well. And then we've got the maximum building masses for wall framing. So all this information in these tables is listed here for us. In this particular case, kilograms per square metre. And there's our building masses for roof framing. So sometimes we've got to work out what weight is going to go on top of the building. And here we can see it all. For example, for a sheet roof, rafters supporting roof loads only, we've got 20 of something. And it's 20 kilograms per square metre. And we can work our way through being able to solve some of those things there. There's another little chance for you to get a green box. In this particular case, you can type into this green box, and it's saying there, refer to 1684 shown below and answer what's the maximum building mass for a wall frame sheet roof supporting single or upper story load bearing. Now, this is going to take you a little while possibly to download that standard and find that, but you can see now where you can get it. Basically, if you go to 1684, and that's 1684, and you're going to need to go to 0.4, and if you go through to 1.4.11, page 10 and 11, you'll be able to type in the answer there to that particular forum and get yourself another little green box. So this is pretty straightforward, this last little bit, and then I'm going to open it all up for you. Just looking to see if we've got anything else that I need to deal with at the moment. No, we're all pretty right. So pretty much this last little activity here is let's look at a typical wall system. So you can see there's a build right, another build right activity, and if we go through to the build right one, it's got walls here. Where are we? Structural properties for walls. Here we are, wall systems down the bottom. And if you look at walls, you're going to know all of that off the top of your head because most of you are builders. But if you don't come from a building background, then definitely jump on here and have a little read through this activity. and you can see there's wall systems, and it talks about timber wall framing. So there's an example of some of the definitions. This is taken from Australian Standard, and it talks about the different parts right through there. So designing a wall framing member tells us a little bit about how to design one. We can see that's where that comes from. What about noggings or bracing? A new change come out recently for noggings, which I'm not sure if you're on a subscription list or not, but there's a little bit of a change to it. It's not going to affect you that much, but the latest standard will have it in there. Pretty much, I'm not quite sure what it had earlier, but your nogging doesn't have to be the full width of your studs, and it can be, but it can't be skinnier than a certain measurement. So here we've got examples of, you can see here pretty much how all this works, and it's got plenty of information there for you on wall framing, especially if you're not real confident with wall framing. Now, just have a real quick look at this before I open everything up for you, and then I shut up. You can see what we've pretty much got here is with bracing, bracing provides the strength for the building so it doesn't fall over. And bracing is pretty much going to be designed according to the wind load. You can see here's an example of some wind loadings, N1 to 4, and that gives us our speeds of our winds. This gives us an example of the effects of the forces. There's a look at some of the different bracing systems. So, and then the bracing actions. Okay, then we've got the bracing action of what it does. We've got to uniformly distribute that bracing throughout a building. Otherwise, the ends might be strong, but the middle might blow over. Okay, we have temporary bracing and we have permanent bracing. Temporary bracing is supposed to be 60% of the final structural strength of all the permanent bracing. So you've probably all seen funny videos of buildings that have fallen over because they haven't quite fixed up the bracing. But you'll find in the code there it talks about 60% of the permanent bracing required before you leave each day for the particular wall. There's an example of some temporary bracing. We are now allowed, as of 15 years ago, which is not very current for you all, but I remember the day before this happened, we are now allowed to claim the plasterboard or the villa board as part of our bracing, up to 50% of what we are required. So the benefit of that is that we don't have to have quite so much bracing in a building because the lining on the building actually helps us. Now, this is real helpful for you. So if you like some of these pages, as you're looking through, just pop them on your star with your little star up the top and pop them on your favourites tab, because pretty much what you've got here is going to help you with your assignment in case you can't read the Australian Standard. But if you look at the Australian Standard 4055, there's a clause right there. Remember, that's 2.2. And that clause there, following those 4 steps right there, is your assignment. If you do those 4 steps, that's one of your big assignments that you're going to get opened up in a couple of weeks' time for you to do. And so pretty much here it is put into 7 steps instead of 4 steps. And it just tells you a bit about how to design it. Look at that. Determine the wind classification, determine the wind pressure, area of elevation. So you've got to do those things, and you can follow them through one at a time and make sure that you meet all that criteria, and that'll be real useful for you when you do your bracing. Down here, we've got fixings and tie downs. We're also going to do an assignment on that. And so that gives you an example of how that works. That's just some good background information, because I know we have a few students here who may not have a background in construction. So you can read through all of that and have a look at that. And then there's an activity there for you to go through if you just need a bit of extra help, just to, because these ones are quite good because you can actually put an answer in there and check it. I just guessed and got that one right. But if you're not quite sure, you can go through and just see how your learning is going on those little build right exercises. So I've popped them up there on my favorites for quick reference while I'm doing this. So there's another activity here for you to do with wall systems. And this one you can type into in a second. And that's pretty much going to say list 6 different types of wall systems. Now, that is kind of a little bit confusing, but if you look at the Australian Standard and you do a little bit of research through that toolbox that I showed you, that will give you some of the different sorts of wall systems. There's also some quizzes here that I'm going to open up for you, and that's pretty much everything from tonight. So there's a bit of a quiz there for wall terminology. Opening everything up now, there's a quiz there for design tables and floors.